This is AB Calculus section 6.3, days 1 through 3. We're going to talk about finding volume using the disk washer and cross-section method. We got 3 days on this. I don't know if we'll be working with 3 days of actual time, but if we were to, I'm trying to write on this and it's not helping. Day number 1 is going to be disk method. This will be examples number 1 and 2. Day number 2, washer, which would be 3, 4, and 5. Oops. Examples 3 through 5. Okay, and day number 3 will be a cross-section volume, which will be example number 6. So this video specifically will focus on the disk method. Okay, so let's get right to it. The definition of a volume of a solid. Okay, given A of X, which is the cross-section area of a given solid, then the volume from X equals A to X equals B is given by the following integral. Okay, we would integrate from A to B of A of X dx. So, for example, like here's a classic example of an area function, right? So let's take and let's just take a simple function like some linear function like this, and let's create a solid by revolving each of these values along this function around the x-axis. So you can imagine, right, that we would end up with this almost cone-looking shape, right? So A of x would be some kind of circular function. Okay, now in its simplest form, right, we could see this show up very clearly. Right, if this was a constant, right, we would actually get a cylinder. If I were to rotate this around the x-axis, and this isn't as good as my first one, but it'll do. And we get a cylinder. So let's say, for example, we integrated from, let's say this was, the point, I don't know, let's say this was A1, and this is A negative 1 out here to B negative 1 and B positive 1. Okay, so what would we really be doing? Well, A of x, right, is this circle. Well, if I were to kind of pull that out of there, right, where you can imagine, like, here's the x-axis passing through there, and this is the point A1, and this is the point A negative 1. I really have an area function, right, A of x equal to pi times 1 squared. So my function is really just pi, right? Okay, so I would integrate from A to B, and let's give A and B values. Let's call A0 and B5, right? So imagine a cylinder, right, that had a base radius, right, of 1 and a height of 5. Well, we know in geometry that the volume would be pi times r squared times h. So what we should get is pi times 1 squared times the height, which of course would be 5 pi. So over here, if we were to integrate from 0 to 5 of pi dx, we would get pi x from 0 to 5, and go figure, when we use FTC part 2, we would end up getting 5 pi minus 0 pi, and looky there. All right, so that's about the simplest of the examples, but you can see how a of x shows up. Let's look at an example below. So in finding these volumes of solids, the suggestion is to sketch the solid and a typical cross-section. So in our example above, the cross-section was a circle, right? Find the formula for that cross-section, find the limits, and then integrate. So let's sketch and do a couple of examples here. Consider the region bounded by the curve y equals negative x squared plus 4x, the x-axis, and the line x equals 3, rotated around the x-axis. Okay, so let's do a quick sketch. Okay, so step 1 is sketch the solid. All right, so here's x, here's y. Y equals negative x squared plus 4x. Well, if you look at that a little more closely, and you were to take out a negative x, right, you'd be left with x minus 4. So my two x-intercepts are actually the origin, right, and this point x equals, well, actually let's put it like this, 4, 0. Now I don't necessarily need that 0.40 though, because I'm only bounded from, let's see, x equals 0 out to x equals 3. So I'm bounded out to here. Okay, so I'll put x equals 3 right there. Well, the curve itself would look kind of like this. Right, it would look like, oops, that's not well done. Let's try that again. And one more time. Stop there and then dot the rest. The reason for stopping there obviously is that we hit our limit right here, right? So I'm going to take this space, and I don't want to color in there because it'll mess up my sketch, but this space right here, right, bounded by x equals 3, and I'm going to revolve that. Okay, I'm going to do my best here. And let's go like that. Let's see if we can make this look decent. Okay, so you can imagine revolving the portion of that function that's above the x-axis. Right, it will look kind of like this. It's not perfect, but it'll do. It's kind of like a top or something. Okay, I'm going to try to give it a little bit of perception here. Perspective, whatever. Okay, so if I were to look at that from kind of like standing on the x-axis looking this direction, I would see circles, right? I would see circles. That's not a good circle, but there's the x-axis, right? And this length, regardless of where I end up, right along here, regardless of where I end up right there, the radius of the circle would be whatever the output is, right? So you can imagine, like, if I were to draw a line like that, regardless of where it is, that would be this length here, which would be r. And so r is going to equal negative x squared plus 4x. So I've sketched my function, or my solid, and I've seen a typical cross-section. Let's find an area formula for a of x. So a of x, of course, is a circle. So I want to take pi times r squared. There is a of x. Okay, I'm going to find my limits of integration. Those are going to be from 0 to 3. And then I'm going to integrate. So let's integrate this. 0 to 3 of, don't forget, the pi times our function squared. Okay, let's look at how messy that is, and we'll see if we actually want to use the calculator and do a little math 9 work. oops, let's write this out. 0 to 3. That would be x to the 4th minus 8x cubed plus 16x squared. That's not too bad. We'll see how ugly it gets here. This would be x to the 5th over 5. Oh yeah, it's about to get ugly. Minus 2x to the 4th. That would be plus 16x cubed over 3. Evaluated from 0 to 3. That's not as bad as I thought it would be, but it's still not great. Alright, I would suggest doing this with a calculator. I'm going to continue mission here and just finish it off, but this would be the volume, whatever this ends up being. If I plug a 0 in, clearly I'll get 0, so 3 to the 5th is 243 over 5 minus 3 to the 4th, which is 81 times 2, which is negative 162, plus 27 times 16. Oh, that's terrible. I don't know what that is. Well, apparently it comes out to be 144. I used my calculator, I'm not gonna lie. Okay, so it looks like I get 243 over 5 minus 90 over 5. I think that's what 18 is. 18 times 5. Yeah, and 243 minus 90 is 153 over 5. So this would be equal to 153 pi over 5 units cubed. Okay, let's look at a second example here. Our last example for the disk method. Okay, let's continue with the disk method, considering the region bounded by the hyperbola x equals 2 over y, the line y equals 1, the line x equals 0, and the line y equals 4, revolved around the y-axis. Okay, so let's consider this in quadrant 1 and look at what would happen. So let's do a little sketch. Oh my goodness, get a straight line. That's better. Okay, so here's x equals 0. Oops, that's not at all x equals 0, sorry. Here is x equals 0. Let's make a line here at y equals 1. We'll make another line at y equals 4. And a good way to visualize this is actually to look at, right, like how do the lines y equals 1 and y equals 4 relate to the hyperbola? So, for example, if x equals 2 over y, what I would do is just take, for example, when y equals 4. Well, when y equals 4, it looks like x equals a half. So we would have some like point of intersection right here at the point half 4. Okay, same thing, except now let's consider when y equals 1, what looks like x would equal 2. So when x equals 2, then we get this point 2 comma 1. Okay, so what is the function going to look like? Well, the hyperbola x equals 2 over y looks kind of like this, right? I'm not worried about the dotted portion above or the dotted portion as we approach the x-axis. All I'm worried about is that solid portion of the graph. Okay, so I'm going to revolve this around the y-axis. So I'm going to kind of take these symmetrical points. I'm going to create this almost like a volcano looking space. Okay, and you can see again, we're going to have this disk method kind of showing up and being created. Okay, so let's create our area function. Actually, in this case, it's not going to be a of x, it's going to be a of y. So let's take a look as if we're looking down on this figure, right? Right, our circles are increasing in radius throughout, right? But regardless, right, you can think of this as our radius. And regardless of how big that radius is considered to be, we know that that value, that x value, is equal to 2 over y. Okay, so a of y is equal to 2 over y. Now, we haven't really considered, actually that's my fault. I goofed that up, that's not true. This is actually going to be r. R is equal to 2 over y. Therefore, a of y isn't 2 over y. Oh gosh, I won't get rid of that. Okay, let me just scratch it out here. So a of y isn't 2 over y. A of y is pi r squared. Okay, so there's our area function. Now we're going to set up our integral. Okay, so the volume that we're seeking is going to be pi times the integral from 1 to 4 of our area function with respect to y. Let's do this one by hand and just see what we get. Okay, so this would be the integral from 1 to 4 of 4 over y squared. Now I'm going to write it as 4y to the negative 2 dy. Okay, let's find the antiderivatives. That'll be pi times negative 4 over y evaluated from 1 to 4. Okay, let's take a look here using FTC. That will be negative 1 minus negative 4. This is kind of pleasing. Very nice. Looks like we would get a volume of 3 pi units cubed. Very good. Guys, that's disk method. We'll see you in the next video for some washer method. Have a great day.